Hi, welcome to today's video. I'm Chantel Pohl with Salt Spring Fire, and today I have my firefighter helper, Hayato, who's going to be running our hoses for us. So he's dressed in his firefighter gear as opposed to me. Today's video, what we're going to be talking about is something called friction loss. And basically what that is it's the reason why we use different sizes of hose. So I'm going to show you the different sizes of hose we use and why we use big hose or small hose. And that's going to be talking about friction loss, which for me is when I joined the fire department and started figuring this out, I was like, hey, math is actually really important. This is why we need math. So I know when I was in school learning math and I'd sit there at the desk and be all bored and I'm like, when am I ever going to use this math stuff? This is when we're going to use math stuff. So we use lots of math to try and figure out what kind of water pressure we need depending on the size of hose and kind of complicated formulas. I'll try and keep it simple. So starting with our big hose is the type of hose that we're going to have coming off of our fire hydrant over here. So here we have a standard fire hydrant that usually have two attachments on the side. And today we've attached a single, it's called a 4-inch Storz off of the main connection, and that's what's going to our truck. What this is going to allow us to do, so here we have this hose coming along and it's going into the side of our truck and it's what's filling our truck, filling the pump with water. This hose is really heavy. Let's see if I can try to move it. There we go. I can move it, but it's not really practical for moving around and trying to maneuver around stuff. What it's good for is to be able to move a lot of water pretty efficiently with very little friction loss. Then we have over here, I have two other side hoses connected to my pump panel. So here I have a 2.5-inch hose. And this is also, it's a bit heavier, but it's going to move a lot of water. We call this big water. It's a 2.5-inch hose. And then here we have a 1.75 line, so it's a bit smaller. This one is way more, the most easy to maneuver around and really easy, but it's going to move less water because it's a smaller hose. So I'm going to show you a little bit about friction loss. I have a little experiment over here. So I like to think of friction loss. If you think about the size of your hallway at your home, it's probably, that wide, give or take. And it's for being able to fit a few people at a time through the hallway. The hallway at your school is probably wider than that because it needs to be able to fit more people through the hallways. If you've ever been to a sporting arena that has thousands of people, those hallways are corridors are massive to move big amounts of people very efficiently. That's the same principles why we use different kinds of hose, not necessarily for how much pressure we can put on, but how much water we can move efficiently. So big hose, big water, we're going to move really efficiently, and a smaller hose, we can move it around more efficiently, but it's going to move less water. Another kind of experiment that's going to show that is here I have a funnel, like a hallway. I have some rice. Those are my people, and if I try and move this many people through this little hallway, we'll see how fast they can get through there. Now we got some congestion, so it's kind of some of the people got stuck. And I can convince them, like, hey, people, move along, move along. There we go. We got all the people to go through the hallway. We move up a side, get a little bit bigger hallway. Still going to try and move the same amount of people through it. Got my people, trying to get my people through that hallway. And they're going slowly. Oh, they're a little congested at the end. Not as much congestion. And all the people get through the hallway. Now if I go up one side, and we didn't have any congestion in that big hallway, which is why we're going to have big hallways in sporting arenas to have the least amount of what's called friction loss. So to figure out friction loss is like a really complicated formula. We have this wonderful, we call it a cheat sheet because, we don't need to think of all the math. So this gives us some of our basic numbers that we're going to use on an ongoing basis. And then we still have to add some of the numbers ourselves. So we'll have to add if there's any elevation change, if we're going up or downhill, that's going to change things. If we've added appliances, just kind of a water tool. and our nozzle pressure, and then we figure out friction loss. That way we figure out what pressure do we need to start at so we can end up over there with the right pressure. So we still have to do some math, but the friction loss has already been calculated for us with a lot of the things we often use. And if we're using something different, then we'll have to calculate it ourselves. So we'll show some of this water flowing so you can see the water moving. Okay, I was gonna fire up our 2.5-inch hose, and he'll move it around a little bit so you can see it's a little heavier and harder to manage and move. We'll just let this lovely gentleman walk past so we don't get him wet. Get a pretty good amount of water out of that hose. And how easy is that to move that hose, hey Otto?
It's pretty hard. It's very heavy, and there's a lot of water though.
Okay, and now let's try the 1 3/4-inch hose. So that one's gonna be easier to maneuver. We get a little bit of less water out of it. But it's a lot easier for Hannah to just pick that hose up, move it around. He's not gonna have to be fighting with it as much. Usually we would use 2 people on the 2.5-inch hose. So that's friction loss. That's why we use different kinds of hoses. And that's why math is really, really important. Does anybody have any questions?
If you have any questions, you can put up your hand. Robin, you have a question?
Why is math important for that?
Why is math important for that? Because I have to do the adding, I have to multiply. In order to figure out my friction loss, I have to do a bunch of multiplications with the friction loss formula, which is something you learn in like high school grades. But even if I already have, even with my cheat sheet, so for this application, say I wanted to have, it's gonna tell me to figure out my discharge pressure, which is the pressure I want the pump to put out, which this hose here is showing I have a discharge pressure of 90, plus any elevation or minus. I don't have any, so I can put a 0 there, plus any appliance, if there's any appliance pressure. I don't have any appliances, so yay, I get to throw another 0 in there, and then plus my friction loss. So to figure out my friction loss, I have to look at my chart here and figure out which hose I'm using. I think it might be on the back of that chart. So I have a 1 3/4-inch hose per 100 feet. So I only have a 50-foot length of hose here. And and then it depends on how much water I'm moving. If I'm doing 95 gallons a minute, and that means I'm doing 95 gallons of water, that's like almost 400 liters of water every single minute. That means that I would be losing 7.5 PSI of friction loss in this hose. So if I start with 90 here, that means Hayato on the other end is gonna get 7.5 less. So he's only gonna get 82.5 PSI on the other end. And if I wanted him to get 90, I would have to bump this up, and I'd have to start this with 7.5 more PSI so that he still gets the PSI, the pressure on his end of the hose that I want him to get. That's where I have to do all that math in my head really fast so that he makes sure that he gets the right pressure at the end of the hose. And if there's really long amounts of hose and I'm moving lots of water, that's gonna mean more friction loss, and that's gonna mean the math is really important, because I don't wanna think that I'm sending him 100 PSI of pressure here, and he's only getting little 10 PSI on the other end, and he's feeling like it's just a sad garden hose on the end, and he's not gonna be able to put up very much fire. So I wanna make sure he gets the right amount of pressure at the end of the hose so he can put out the fire and do his job. That's why math is important. It's a great question, Robin.
Does anybody else have any questions? You can just put up your hand or unmute yourself.
Hey, Hayato has a question.
I have a question, Chantal. So what if my team is 4 stories up on a building? How would you calculate the friction loss there?
That's a great question. So I would have to calculate based on my elevation. So here my little cheat sheet says number of floors minus 1 times 5. So now I have to do a bunch of multiplications. Okay, so I have 5 PSI per floor. So if he were on the 4th floor, and with this hose, we already figured out, okay, he's losing 7.5 PSI of pressure, but now he's on the 4th floor. So now I'm losing an extra 5 PSI per floor. So that means I have to multiply 4 floors times 5 PSI. So that's going to be 20 PSI added to that 7.5 PSI that we figured out was that friction loss through that narrow hallway. So that's going to give me 27.5 PSI friction loss. That means I need to add 27.5 PSI to my pump of my start pressure to make sure that he gets the right amount of pressure on the other side. Great question, Hayato.
Thank you, Chantel.
Okay, I have a question. Do you get more friction loss from a big pipe or less friction loss from a big pipe?
Great question. Just like I showed with the rice, and if you think of the sporting arena with a really big hallway, the bigger the pipe or the bigger the hose, the less friction loss you're going to have. And the other factor is how much water you're trying to fit through that hose. So if I'm trying to fit 100 gallons through this hose and 100 gallons through this hose and 100 gallons through this hose, I'm going to see a different amount of friction loss. This one is going to see the least. But now if I try and push 800 gallons of water through the hose, then the friction loss I'm going to see, because all of those water molecules, if we think of people trying to rush through a really narrow hallway, those are the people that are sticking out their elbows and trying to bump their way past. And the water molecules get really excited. You're trying to push lots of them through a small hose, and they kind of do the same thing. And so the more water molecules are trying to shove through that hose, the more excited and agitated the molecules become, the more they're going to struggle to get through. So there's going to be greater friction loss if we try and push more water through a smaller hose. And the bigger the hose, and if we push less water, we're going to see less friction loss. So there's kind of two factors that add friction loss. Any other questions? So I'm glad you enjoyed this video on quick little explanation on friction loss. I mean, next time you go to the sporting arena, you can be like, hey, these have huge corridors to fit lots of people through, because otherwise there would be lots of elbowing happening, which is why they made those hallways nice and big to fit all of those people. Or you can think about it even at your school hallway. Maybe you could talk to your school and be like, hey, I think the hallways need to be a little bigger for the amount of students you're trying to fit through these hallways. And unfortunately right now with, staying at home, probably don't have a whole lot of issues with friction losses in the hallways at your home school at the current status. But thanks for watching our video on friction loss. Hope you had fun learning about math and friction loss, and math is cool. I'm really happy I got to learn more math with firefighting. I didn't think it would be a thing, but it's actually kind of fun learning math and learning how to apply it in the real world, even as an adult. So thanks for watching today's video. Bye.